Hello students, now in this lecture we will start the module number 1, that is properties of semiconductor, in which the first point is band structure in semiconductor. In an isolated atoms, when brought together to form a solid, various interaction occurs between the neighboring atoms. The forces of attraction and forces of repulsion between the atom will find a balance at the proper interatomic spacing for the crystal. In this process, the important changes occur in the electron energy level configuration, and these changes result in the varied electrical properties of solids. We will see the example of silicon. So, silicon atom has the electronic configuration which is 1s2, 2s2, 2p6, 3s2 and 3p2. So, in this electronic configuration of silicon, this 3s and 3p are the valence electrons. These 4 electrons are valence electrons, and these electrons interact to form 4 hybridized sp3 electrons when the 2 silicon atoms come closer. We schematically show the Coulombic potential well for the 2 atoms closer to one another, and in that Coulombic potential well we may draw diagram. So, in this Coulombic potential well, when we see there are 2 possibilities of finding this interaction of energies, that is, when 2 silicon atoms come closer, there is possibility of finding the 2 electron wave function which combining, that is the electron wave function of silicon atom, that is first atom and second atom combining together, and which forms the linear combination of atomic orbitals. And there are 2 possibilities, that is, one is the odd combination and another one is even or symmetric combination. So, with even combination we find the bonding orbitals, and with odd combination we find the antibonding orbital of respective valence electrons. When they combine together, there are these 2 possibilities, and the even combination is called bonding orbital, and odd combination is called antibonding orbitals. It can be seen that the bonding orbital has higher value of wave function than that of antibonding orbital, and therefore this bonding orbital has the higher electron probability density. To determine the energy levels of bonding and antibonding states, it is important to recognize that the region between two nuclei, that is when electron come in between the region between two nuclei, the Coulombic potential energy is lowered as compared to the isolated atoms. This is because when the electron come in between the region of two nuclei, there is forces of attraction which is applied due to these both nuclei, and due to which the Coulombic potential energy get lowered, and this lowered energy due to existence of electron in between two nuclei is much lower than that of the isolated atoms. That is, the energy which is found in the isolated atom is much more than in the case when the electron is found in between two nuclei. Again, for the antibonding orbital, as the two electron wave functions combine together antisymmetrically, the energy is greater than that of isolated atom, as well as in case of the even combination of atomic orbital or even a combination of wave functions of the atomic orbitals, and it is because the interatomic distance between two atoms is much lower, and due to which there is increase in repulsive forces between the two nuclei, as well as the repulsive forces due to the electrons of the two atoms, due to which the Coulombic potential energy is much higher than that of the bonding orbitals in case of antibonding case. So we see the antibonding orbital has the much higher energy than that of the bonding orbitals when the electron is found in between the two nuclei, and the potential energy for the bonding orbital is much lower than that of the antibonding orbitals. Qualitatively, we can see that the atoms are brought together, and there is need to apply the Paulis exclusion principle, which is very important when two atoms come closer. When two atoms are completely isolated to one another, so that there is no interaction between the electrons of the two atoms and the electron wave functions between them, so that these two atoms, when they are isolated to one another, these atoms have the identical electronic structure. As the spacing between the two atoms becomes smaller, the electron wave function begin to overlap. The exclusion principle dictates that no two electrons have a same or identical quantum states. Thus, there must be at most one electron per energy state or per quantum state. So, there is splitting of discrete energy level belonging to pair of the atoms into the new energy levels rather than the individual atom. That is, when electron come together due to or by applying the Paulis exclusion principle, when two silicon atoms come closer, these atoms have different quantum states, due to which these atoms have different energy levels when come closer to one another, and due to which there is possibility of formation of bonds, band structure. So in a solid, when many atoms are brought together, so that there is splitting of energy levels which forms the continuous bands of energy. So this figure shows the formation of band structure when two silicon atoms are apart from each other. Then as the 3s and 3p are the valence shell for n is equal to 3, 3s and 3p are the valence levels for these silicon atoms which are isolated from one another and has the 2n states and 2n electrons in the 3s level and 6n states and 2n electrons for the 3p states. Let's consider this is the electronic configuration. If we consider the two silicon atoms which are come closer, then there are, for single electron there are two 1s states, two 2s states, 6 2p states and 2 3s states and 6 3p states. That is, these much are the energy levels which are available for these states for a single electron. When two silicon atoms come closer, then these energy states get doubled when these atoms are isolated. If one considers the n number of atoms are come closer, then there are 2n energy states which are available for this 1s state, 2n states for the 2n energy levels for 2s states, 6n energy levels for 2p states, 2n energy levels for 3s states and 6n energy levels for 3p states. When these atoms come closer at particular interatomic spacing, these 3s and 3p levels get combined and we observe the 8n states for 4n electrons. When again this interatomic spacing is decreased at some interatomic spacing, we find there is separation of energy bands. That is, this upper band has 4n states and lower band has 4n states, and these two bands are separated by the energy gap which is given by Eg. That is, in this energy gap there are no allowed energy states are available, so that this energy gap is also called as forbidden gap. And normally at 0k all the electrons are observed in the lower energy band and upper energy band is empty. That is, it has the 4n state but 0 electrons, and lower energy band has 4n states and 4n electrons. So at 0k, when silicon atom is observed, then other than the core levels we have these are the states, and at 0k the electrons will occupy the lowest energy state. That is these states are occupied by the electrons at 0k. So in this case of the silicon crystal, there are exactly 4 4 n states available in valence band and 4 n electrons are in this valence band. So this lower lying band is valence band and upper band is conduction band. So this is all about the band structure in semiconductor. So with this I will stop here. Thank you.